All right, 2.15 semi-log plots. Here we go.
Do we need to start at previously?
Yeah.
Previously in topic 2.9, logarithmic expressions, we looked at the idea of using logarithmically scaled axes to help us better understand that data is, or understand data that is exponential. We now return to the idea, or to this idea to examine it in a little more detail through the semi-log plots. In a semi-log plot, one of the axes is logarithmically scaled. In AP pre-calculus, we will only be scaling the vertical y-axis. With a semi-log plot where the y-axis logarithmically scaled, exponential functions will appear linear.
All right, fantastic. So in our course that we're taking right now, our vertical axes is going to be logarithmically scaled. A lot of the times it will be base 10. However, I guess technically it doesn't have to, but what I've seen is base 10. And then our x-axis, our horizontal axes, is going to be linearized. Just like normal, this is normally how we look at things, and so forth. All right, this is what I need you to like star, remember, circle it. Okay, this is what we're focused on. Exponential functions will appear linear on a logarithmic scale axes. All right, on a semi-log plot, exponentials will appear linear. All right, that's kind of like really how we're going to be tested on multiple choice type things. All right, Caroline's going to keep going.
Previously, we looked at the two graphs displayed above, displaying the population of English Americans in the current United States from 1620 to 1820, where t equals 0 represents the year 1620. The graph on the left shows the population using a normal scale on the vertical axis. The graph on the right is a semi-log plot where the vertical axis has been logarithmically scaled. Example 1. Use the features of the semi-log plot above to justify why an exponential model is appropriate for the population of English Americans in the current United States from 1620 to 1820.
All right, beautiful. So this is our normal scaling. All right, so it's not logarithmically scaled at all. What kind of function does this look like? Exponential. Looks like exponential growth. All right. And so when it was semi-log plotted, when I had it logarithmically scaled on the vertical axes, now what kind of function does it look like? It looks what? Linear. And so what we need to say there is that a semi-log plot seems to be what? So the semi-log plot is appropriate because why? Because it appears linear. That's great. Because the exponential appears linear. All right. And so in physics and such, they try to linearize data, and so they'll actually go with these kind of plots. All right. All right.
I got you. After Mr. Passwater tells another one of his hilarious math jokes, it begins to spread around the school. The number of people P that have heard the joke after T minutes is graphed on a semi-log plot above, where the vertical axis has been logarithmically scaled. Which of the following functions could be a model for P?
All right, fantastic. So let's look at this semi-log plot. What do we notice about the semi-log plot? It's linear. All right, so it's linear. And so if it's linear, then it knows it's a what kind of model? Or what kind of function was it? It was exponential. So what two problems can I get rid of right away? A and C, exactly. All right, so we can get rid of those because those are not exponential. Now I'm between B and D. And this is the way that I personally would like you to go about this problem. Not all teachers will tell you to do it this way, but I think this is good enough for this class. So I kind of would like to just substitute in. So right here, what would this ordered pair be? 0, 2. Be 0, 2. And so when I substitute in 0 right here, what do I get? 2 plus 1, because 2 to the power of 0 is 1. And so this would be what? 3. What would I get on D? I'd get 2. So which one is it? It's D. Now, there's a couple other reasons why I really want you to pick D instead of B. All right, yes, the substitution thing worked, and that's a really good way to do it. However, there's another way that I want you to think about it. Remember when we did exponentials, we had this y equals abx form? You guys remember that? And so the D one fits that exponential form rather than this one. This 2 actually did what? It vertically shifted that one. All right. And so, yes, that we could think of it being vertically shifted, and yes, that could work out. However, it's probably going to be more likely to be in that AXB or ABX form. All right. Let's keep moving. Robert, pick somebody.
Important note about semi-log plots. When we logarithmically scale the vertical axis for a semi-log plot, we are not changing the actual y values of the data. To logarithmically scale the vertical axis means that equally spaced values on the y-axis are proportional, whereas equally spaced values on the x-axis are linear.
All right, good. Keep going.
Example 3. The table above gives selected values for the function f. Which of the following graphs could represent these data plots in a semi-log plot, where the vertical axis is logarithmically scaled?
All right, beautiful. So I've looked at a somewhat decent amount of these problems. Which 2 are not logarithmically scaled, first of all? Which 2 problems on these are not logarithmically scaled? C and A. Those are not logarithmically scaled. All right. C is like our basic normal one. A has something weird with our x-axes. All right. And so then my vertical axes are being changed on B and on D. However, which one makes sense for this data set? D. All right. Dear goodness, my lowest value here is 40. And so does this one even go up to 40? No. All right. And so that's how we'll be tested. I honestly think that's going to be an easy multiple choice problem on your AP exam if we actually understand what logarithmically scaled means. All right. All right. Let's keep going. So on this one, we're going to start plotting. And I'm going to go basic, and then I'm going to go a little bit more difficult as we kind of move. And so if I graph this first one, 0, 200, 0 would be right here, and then 200 would be up there. And so we've kind of done these before in section 2.9, and so I got 0, 200 there. And then let's do B. And so B is 1, 25. And so if I do 1, 25, this would be 20, and then this would be 30, right? However, 25 is not actually right dab in the middle. It's actually a little bit more, like, it's a little bit higher than the middle. And I want to try to reason this out with you. If I'm like smack dab in the middle, okay, if I'm like smack dab in the middle right there, like I'm just going to call this like 5, something. And so there could be like 5, 15, 5, 13, or like 5, 17. Okay, this is going to be kind of like a problem on your test, possibly the AP exam. Which one is it? Is it going to be 515, 513, or 517 if it's smack dab in the middle? It's actually going to be 513. Exactly. And here's why. Here's why it's going to be 513 and not 515. Do you see the gap between like 10 and 20? It's really big, right? And so then when we start going up, my gap like decreases. Okay? And so my gap between like 100 and 90, very small. Okay? And so if I actually need like 1, 25, I'm actually further up than the center. All right, so on 2-7, 2-7's kind of nice because 2-7 is right on one of them. And so what are we at? 9, 8, 7, right there. All right, and then 3.2, 800. And so what are these spacings? They're by what? 0.2. And so 3.2 is that first spacing, and then all the way up at 800. And so we're kind of right there. And then 4.6 is which dash? It's my third one, all right? And so it's my third one, and then 1.5. Now, is 1.5 smack dab in the middle? No, it's actually a little bit higher than in the middle, all right?
All right. As we have seen, if we graph an exponential function on a semi-log plot, the graph will appear linear. In these cases, we can create a linear model for the graph on the semi-log plot. Linear models for a semi-log plot. Given the exponential model y equals ab to the power of x, the corresponding linear model for the semi-log plot is given by y equals that stuff.
Log base n of b.
Log base n of b x plus log base n of a, where n is greater than 0 and n does not equal 1. Note number 1, the slope of our linear function is log base n of b, and the y-intercept is log base n of a. And note number 2, the base n corresponds to the base used for the scaling for the vertical axis.
All right, fantastic. So a couple things real quick. Most of the time they're going to be in base 10 system. Okay, so it's going to be our common logarithmic. I don't really foresee them changing that too much. And so your base n is going to be a 10. All right, more often than not. But then it's just a line. All right. However, the hard part about this is that it's going to be logarithmically scaled for my vertical axes. That's going to be the hard part for us. All right. And so this is a line. Yes? What do all lines have? They have slopes. They have slopes. All right. And so what do we need to do to find our slope? How do we find slope between 2 points? Y2 minus y1 over x2 minus x1. And so this is what's called an average rate of change. Remember that? So our average rate of change, I need to find between 2 of these points. Now, I'm personally going to pick these first 2 because they seem to be nice and easy for us. All right? And so I'm going to pick this one, and I'm going to pick that one. And so I need to find my slope between those 2 points. Now, this axis is what kind of scaled? Logarithmically scaled. And so what I need to do is this is going to be like my y2. And so this is at what? 10, 20, 30, 40, 50, 60. 60, right? And so this is actually going to be log of 60. And then minus, now my y2 is going to be what? Log of 40. Over my x-axis is the same, and so now I have just 2 minus 1. All right, so now I ended up finding my log base n of b is equal to this 0.17609 blah, blah, blah. All right, pretty good. And so now I end up having the equation of y equals 0.176091259 x plus my y-intercept is basically this log base n of a. All right, and so now I need to solve for my y-intercept. Okay, and so now I need my y value and I need an x value. So pick one of these points. Does it really matter which point we use? No, it doesn't really matter which point you use. You want to use this one? All right, Jackson wants to use that one, and so we'll use that one. All right. So on that one, my y value is not 40, but it's actually what? Log of 40. And that's equal to this 0.176091259 and then my x value is what? 1. And then plus log base n of a. And so what we need to do to solve for log base n of a is take this and subtract this product. All right, so we're going to take log of 40 minus this. All right, and so let's do it. All right, so on our calculator, I'm just going to press in log of 40 and then minus. Now this is where I like to use my copy and paste feature. So remember how to copy and paste? Okay, I like to use this one because it's a lot easier too. All right, and so now I have that. Oops, I should probably put parentheses around that. That's not going to be good. All right. And then I press enter. And so now we basically have our y-intercept. All right, and so now my log base n of a is equal to this 1.4596, whatever. All right, and so my equation, we'd have y equals this 0.17609 dot 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 x, and then plus 1.42597 dot dot dot. All right, and so there is our equation of my linear function. All right, now let's look at part B. And so part B, it says, okay, we're going to use what we found in our linear, and then we're going to make it into the exponential model. All right, so now we're going to find this A and our B. All right. However, what happened to these problems? They were what? They were logarithmically scaled, right? And so what was my base on those? 10. And so to solve for A, we'll just use A first. To solve for A, we're going to do 10 to the power of what my A was. And so now I'm going to do 10 to the power of 1.425968732, so forth. All right. And so now I'm going to kind of use my calculator to cheat a little bit. And so now I'd have 10, and then to the power of, and then I'd like to copy and paste whenever I can. All right, instead of using all that, I'm just going to go into that, and I'm going to copy it, and then I'm going to paste it. So now my A would be this 26.6 repeating. All right. So now to find my B, again, this is already logarithmically scaled, so now I'd have 10 to the power of what my log base 10 of B is. And so then I'd put that to the power of this 0.176091251. All right. And so again, I have a calculator that can do cool stuff. So I'm going to just say 10 to the power of, and then I'm going to grab my B, which is that one, and then I'm going to press enter, and that one plays super duper nice. And so now I have B equals 1.5. All right. So now my equation will end up being y equals 26.6 repeating times 1.5 to the power of x.